Hello, everybody. Welcome to the Kallanish Hydrogen for Steelmaking webinar. It's a pleasure to see so many attendees from different parts of the world. We've had an amazing turnout with over 700 registrations, which shows hydrogen is a very hot topic. Thank you for joining us. I'm Gabriela Fahanghi. I am the European editor of Kallanish Power Materials, which is a sister publication to Kallanish Steel. And we cover battery materials, electric vehicles, and hydrogen. And obviously today, we'll focus on the hydrogen application for the steel sector. And that's why I would like to introduce my amazing panelists here today. Steve Rendell, Managing Director of Kallanish Index Services. Hakon Voldal, CEO of No Hydrogen. Thomas Hernfeldt, Vice President for Sustainability Business at SSAB.
Hello.
And Stefan Tondo, Head of Government Affairs at ArcelorMittal. Welcome all. Thank you. Well, hydrogen is considered a potential holy grail for decarbonizing the hard-to-abate industries, especially steel. The steel industry today accounts for about 7% of the global CO2 emissions and 5% in the EU. And although the steel mills in Europe are highly efficient, there's still a lot of competition. There's a lot of decarbonization for us to go through and potentially transition the traditional blast furnaces into DRI-EAF route. The EU wants to become carbon neutral in 2050, and steelmakers in Europe will have to curb their emissions by 30% by 2030. For that to happen, we need lots of low carbon technologies to be developed and commercialized in the next 5 to 10 years. So I'm sure you agree hydrogen can be an enabler, and that's why we're here to talk about the subject. The format today is going to be very simple. We'll have the presentations. Our distinguished speakers are going to present to us, and then we're going to have a panel discussion after that. And you can submit your questions through the control panel on the right-hand side of your screen at any time during the webinar. Without further delay, let's start with our presentations. Steve, please set the scene for us.
Well, thank you, Gabriela. I hope everyone can hear me okay. So I should say good afternoon or good morning, good evening, everyone, wherever you are in the world. And thank you, Kallanish, for the invitation to speak on this webinar today. We have a great lineup of speakers, as you've heard, so I'm not going to waste any time. I'm going to jump straight into providing an overview of the role hydrogen can play in addressing the challenge of decarbonising the steel industry. The steel industry, as I'm sure everyone is aware, is currently responsible for about 6 to 7% of global carbon emissions. So it's a major contributor. And iron ore reduction with coke in the blast furnace, using that route, accounts for the majority of those emissions, as you can see from the chart below in the center there. Now, about 70% of steel in the world is made this way via this route, although that varies by region. It's as low as 30% in the US, but it's 90% in China. Now, the balance is made via the electric arc furnace route, melting scrap, sometimes including direct reduced iron, and that has far lower emissions, around a quarter of the blast furnace route. So moving away from this blast furnace iron ore reduction using coal and coke, is a priority if the industry is to reduce its emissions, and the DRI process can reduce that iron ore using hydrogen with virtually no emissions, and that's a key area that we're seeing hydrogen being introduced or considered. Now, at the moment, just over half of the major steel companies around the world have published their carbon emission reduction targets to get to net zero by 2050, or in some cases their targets are a bit before then. Here's a selection, and Europe is leading the way. I mean, it does vary by region, but I think virtually every West European steel company has a plan. But in other regions, it is more patchy, it has to be said. And given that the largest companies are going to have the biggest impact on global emissions, then we have I think six of the 10 largest steel makers are in China. So you can appreciate that at the moment, I think it's around 13 of the top 25 steel companies have plans. So there's still quite a long way to go outside Europe for getting all of this in place. And I think even more importantly, perhaps few companies, although notable exceptions, including our guest today, have committed much capital to this so far. In a lot of cases, it's more talk. Now, BF operators, blast furnace operators, can reduce their carbon emissions to some extent by just optimizing their existing processes, and certainly by implementing some carbon capture on off gases and so on, as the table below shows. But if you're going to achieve significant reductions and get to net zero, then it's hard to see how that can be done without investments from companies that have blast furnace routes. And this either means investing in the existing technology effectively of electric arc furnaces, melting scrap and DRI, or looking at new technologies that will enable that iron ore reduction in the blast furnace without the use of coal, carbon and coke. But in all approaches, hydrogen looks as though it's going to play a major role. And whether it's producing green direct reduced iron to go into EAFs or I say through another process. And most steel companies are taking a multi-strand approach, if you like, a phased approach as well. This isn't just jumping to the ultimate solution, net zero with an investment bang. It's just not feasible. So most companies are putting together a package where they're optimizing routes and implementing capture or offset, and then looking to use new technology. Now, there is a whole multitude of technologies that are under varying stages of development out there. As you can appreciate, this is such a big challenge, and there's lots of ways to approach it. And it's certainly not going to be one size fits all when it comes to the adoption either. Specific technology choices are going to be driven by the regions that steel companies are in, and by their access to low carbon or zero carbon renewable power, their access to hydrogen potentially, their access to carbon storage and so on. So it's a complicated arena, and not one that is a simple answer for sure. So if we just focus on the EU for a moment, as I've said, it's pretty much leading the world in the decarbonisation of the blast furnace route. Currently, about 55% of steel in the EU is made via that route. And the map on the right here endeavours to indicate many of those decarbonisation projects. And we're going to be hearing later from SSAB about hybrid and from ArcelorMittal about its various projects. And if we look at them overall across Europe, though, the numbers there show the sort of projects, and some of those projects are named in the text on this slide. The majority, not all, but the majority include investment in producing DRI, certainly with the long-term intention of using green hydrogen as the reducing agent because of the zero emissions that's possible. So if you look at the EU plans alone, just the EU, the DRI capacity additions that have been announced up to 2030, so that's just in the next 7 years, amount to about 34 million tons of DRI. Now, global DRI production last year was about 119 million tons. So you can appreciate that's a significant investment if, and it's quite a big if all of that indeed happens. And there's then significant implications for raw materials, because DRI, as it stands today, the process requires high quality iron ore, over 67% Fe, and about only 3% of the world's supply of iron ore is that sort of grade. So there's plenty of implications around this. Let's just quickly look at some metrics about what the use of green hydrogen as a reduction agent for iron ore actually implies. And I think the key sort of metric to have in mind is that 1 ton of steel production, if you're going to use this route, requires around 50 kilograms of hydrogen. So 1 million tons of steel production requires 50,000 tons of hydrogen. And if you're going to produce that with electrolysis so that it's entirely green, then that's a lot of electrolyzer capacity just for 1 million tons, as you can see from the numbers there, and vast amounts of renewable electricity are needed, getting on towards sort of 5 gigawatt hours to produce that amount of hydrogen. And indeed, quite a lot of water, 450 million litres are required to produce 1 million tons of, well, to produce the hydrogen necessary to produce 1 million tons of green steel. So you can quickly see that the magnitude of the numbers is significant when, if you look at the world, you know, the world produces nearly 2 billion tons of steel, more than half of that in China, of course, and about 1.3, 1.4 billion tons of that is via the blast furnace BOF route. The balance, 600 million tons or so, is electric arc. So, you know, you're getting on for needing, never mind 1 million tons of steel production. It's more like a billion tons that's going to need, you know, to find another reducing agent than carbon for getting to iron. Cost is another key factor. You know, most hydrogen produced today is grey or brown, produced using natural gas and without carbon capture. So, you know, that's, you know, you'll see costs around $1, maybe $1 to $2 per kilogram of hydrogen for that. But once you start adding carbon capture, it gets more expensive, and certainly the electrolysis routes available today at the scales available today, you know, see those costs going up. And you know, we'll hear obviously more about that from other panelists. But the table and charts here show Kallanish Index Services, you know, it's going to be tracking the hydrogen costs for different technologies in different regions around the world, different locations, and you know, this is the sort of ranges that we're seeing for the levelized cost production sort of over the lifetime of the project at the moment. And that cost is highly dependent on electricity, renewable electricity costs. So that's one of the key drivers there. I mean, utilities alone with water and so on as well is getting on for 3/4 of the cost. Now, at the current sort of costs we're seeing there for green hydrogen, that's, you know, going to add up a lot to the cost of producing a ton of steel, hundreds of dollars potentially at this sort of level. So, you know, it's estimated that those costs have got to come down quite a lot as the scale of electrolyzers and so on increases. This can be possible, and renewable energy costs decrease too. Now, regions with, you know, with the natural resources to do this, and that's again back to renewable energy first and foremost, sun and wind, a key, obviously hydro where it's available as well. So these are going to be the low-cost areas to produce hydrogen. These flows aren't just for, you know, supplying the steel industry. These are what are projected by the Hydrogen Council for, you know, all uses, and energy is obviously, you know, the key one here is for hydrogen as well. But what you'll see here is their expectation is that Europe would actually become a significant importer, with the exception of Scandinavia, some parts of Scandinavia at least, you know, importing by pipelines from North Africa and shipping from South America, from the USA potentially as well. Other areas you can see Japan, other parts of Asia, most of Asia in fact, also importing more in those cases from the Middle East, big exporter likely, and America again, South America, Australia and so on. So that's likely to set up significant trade flows for hydrogen if this level of hydrogen is going to be used, this quantity, to decarbonize the industry. So I think the message is pretty clear, isn't it? I mean, green hydrogen can decarbonize the steel industry, but it involves it's going to involve massive challenges. First and foremost, the scale of hydrogen generation that's going to be required. Yeah, go back to that. 1 ton of steel needs 50 kilograms of hydrogen. If you're going to use this approach, then the estimates get you up to something like 52 million tons of green hydrogen per annum. And the world today, I think, is only generating less than 100 million tons of grey hydrogen for all purposes. So you can see the implications there. Scale of renewable energy, obviously vast. Again, according to Wood Mackenzie estimates here, the steel industry alone would need 2/3 of the current renewable energy capacity, and obviously most of that is going into power. The costs we've talked about, and the availability of that high-grade iron ore, if you're going to use the existing DRI route. Now there's efforts to develop those technologies to enable them to be used with lower content Fe, so that that iron ore supply isn't going to be such a constraint. Also increased demand for scrap, maximising the use of that, but that's going to have impact on costs, prices rather, of scrap and trade flows. Big exporting regions for scrap today may be hanging on to that scrap far more, and that'll have implications for regions that currently rely on importing scrap. So those are some of the challenges, and that's before we even talk about the money. There's the investment required, and again, a Wood Mackenzie estimate here. But if the steel industry is going to achieve net zero by 2050, they're putting the costs of doing this for investments in the order of sort of $1.5 trillion US. So that's no small challenge, and you can see most of that going into the iron making, steel making sort of areas. Inevitably, the question is, where's the money coming from? I mean, the steel industry hasn't always comfortably, achieved a good return on its capital. So, yeah, finding this sort of money to make these investments to achieve this is no small question. Right, that sort of wraps up my overview. As I've said, Kallanish Index Services, as Gabriella mentioned, it's a new subsidiary of Kallanish, and it's going to be launching its hydrogen subscription service sometime next year. Kallanish Index Services focuses on the data side of things, and that'll complement the news and other insights that you've already received from Kallanish. And we'll be focusing on those sort of tracking those hydrogen production costs, tracking the projects around the world for ammonia as well, looking at breakthrough technologies where they are emerging to try and change some of the equations that we've seen here about what's required, and so on and so forth. So you can register your interest at callindex.com. I'm afraid you won't find any useful information there yet, but if you like to register there, then you will be lined up for a free trial when the service launches next year. Thank you very much. I'm going to hand back to Gabriella.
Thank you, Steve. Thank you so much. That was really insightful. A lot of food for thought there. Let's now move on to Nel Hydrogen. Hakan, can you please tell us about how green hydrogen can be produced and all about electrolyzers? Please, the floor is yours.
Sure. Thank you, Gabriella. So my name is Håkon Voldal. I am the CEO of Nel Hydrogen. And I'll give a short introduction to Nel and hydrogen for steel making. Now, Nel is a global dedicated hydrogen technology company. We deliver solutions to produce, store, and distribute hydrogen from renewable energy, what we call green hydrogen. And our mission is to unlock the potential of renewables and enable global decarbonization. We cannot be successful without our customers. And as was presented just a few minutes ago, the steel industry could be a big user of electrolyzers and green hydrogen to decarbonize. Just a few facts on Nel. We can actually trace our roots back to 1927 when we installed the first electrolyzer in Norway, and I'll get back to that in a second. But the modern Nel started in 2014 when it was spun off from Equinor, the oil and gas company in Norway, and publicly listed on the Oslo Stock Exchange. We have the world's largest installed base of electrolyzers, roughly 3,500 units in 80+ countries. But bear in mind, a lot of these installations are rather small electrolyzers. We have manufacturing capacity in Norway, in the US, and in Denmark for fueling stations, which we also deliver. We have installed, received orders for more than 100 fueling stations, but that is not the focus of this presentation. We have roughly 600 employees and a global sales network. We have been a preferred partner with industry leaders, not only in steel, but in various industries, as hydrogen is increasingly, being regarded as a solution to decarbonize. And we have raised close to 350 million. We have raised more, but we have now 350 million euro to fund expansion of our manufacturing capacity for electrolyzers. Oops. I would like to start with this. And why do I start with this? Well, this is actually on the left-hand side. You see the world's largest electrolyzer facility ever built. It's not in operation anymore, but the largest electrolyzer plant today is roughly 20 megawatt. It's in Spain, operated by Iberdrola, delivered by Nel. In 1929, the world's largest electrolyzer facility was built in Norway. It was based on hydropower, and it was used to produce ammonia for fertilizer production. And if we're into World War II history, this was the power station that was sabotaged by the Allied forces to stop production of heavy water, which is a byproduct from electrolysis. On the right-hand side, you see the second largest facility ever built in 1953, 135 megawatt, also in Norway for ammonia production. And the reason I start with this is that the scale of what we're looking at, you get an impression by the picture on the right-hand side. This is what we're going to do in the steel industry, times a factor of 3, 4, 5, 6, 7. Most steel factories will need between 0.5 gigawatt and 1 gigawatt of electrolyzer capacity to produce what they want to produce. So the scale up is massive, also in terms of electrolyzers. We are doing our part. We are currently investing in both alkaline technology and PEM technology. We have atmospheric alkaline technology, and we are also developing a pressurized alkaline system. And we are looking at some future technologies that might bring together all the positives of the PEM technology and combining that with the positives of the alkaline technology. But I have to be open, and I can be that because we are a bit technology agnostic. There are numerous technologies out there, and I think it's fair to point out that neither technology has only advantages. They have advantages and disadvantages. It depends on the application. If you want to produce hydrogen at scale today, I would argue that you only have one technology solution, and that is alkaline. Over time, you will have PEM. In the longer term, you will have solid oxide and some other alternatives. But today, only alkaline has been proven and tested at scale. Because if you invest, hundreds of millions of euros into a DRI facility and you want to use electrolyzers, you have to make sure that the electrolyzers actually work. And if you want the plant to run for at least 10 years, maybe 20 years or 40 years, then the electrolyzers should have a similar lifetime. Now, if you buy electrolyzers today, only one company has had electrolyzers in operation for 8 to 10 years. Actually longer, but you know, electrolyzer typically lasts for 8 to 10 years. So you have to scale up what works, while in parallel you try to develop something which is a better mousetrap, a better solution for the industry going forward. We have decided to scale up our alkaline technology and try to use that as sort of the test bed for scaling up hydrogen production for the steel industry. The first step was taken years ago, before actually the steel companies started to consider, you know, hydrogen at scale. We invested in a fully automated production line in Norway, capable of producing 500 megawatts of electrolyzers per year. Then we quickly saw that this is not going to be sufficient. To the points of the previous presenter, you need a lot of electrolyzer capacity in order to decarbonize steel. So we have doubled that now to 1 gigawatt. The second line will be operational from early 2024. And we have the opportunity to double again to 2 gigawatts in the plant in Norway. We're also building out the facility in the US for PEM electrolyzers, knowing that it will take a bit more time to mature that technology. And we are considering a 4 gigawatt plant in the US, you know, bringing that capacity to 6.5 gigawatts per year, which is massive compared to what is being produced today, and bearing in mind that the world's combined or total installed base of electrolyzer capacity, what is running right now is less than 1 gigawatt. So Nel alone will produce 6-7 times what is, you know, has been installed up to now. The automation part is important. When we go back to the cost figures in the previous presentation, our challenge is to both make the electrolyzers available and to bring the cost down. We have set a goal of bringing the cost of green hydrogen down by 75%, meaning we will be at parity with gray hydrogen. Of course, that depends on the gas prices, but it's really the relative difference between gas prices and green hydrogen that matters. So if gas prices are high, then typically power prices are also high. So if you get it down to $2 per kilo, I think it will be at cost parity in a lot of regions with natural gas. And going forward with increasing optimization, with higher scale, with technology breakthroughs, you can get closer to the $1.5, maybe $1 per kilo. We have brought down the cost of our alkaline technology by 50% from a couple of years ago. It will come down significantly in the years ahead as we continue to automate, and hopefully that will enable steel producers to produce green steel at an affordable cost. Now, a couple of examples of what we have done. We have been involved, and I think SSAB will talk about this later. We have been involved in a pilot project in Sweden where we replace coal with green hydrogen to produce the world's first fossil-free steel, and that was done in August 21. It's a 4.5 megawatt alkaline electrolyzer pilot. We're also building a 20 megawatt alkaline electrolyzer to pilot Ovacco's steel recycling. It will be the world's first use of hydrogen and oxygen in the heating process, and the hydrogen production is expected to start in the second quarter next year. And the conversion to green hydrogen will cut CO2 emissions from current levels by 50% in that process, the steel recycling process. So interesting developments, but bear in mind we are in the scale-up phase, and I guess the panel debate will focus a little bit on what can we expect going forward. What I wanted to conclude on is that we are doing our part in terms of raising capital and building out capacity so that you can have electrolyzer capacity for steel projects, and also bringing down the cost to make it affordable.
Thank you very much, Håkon. That was really interesting, and I'm sure you're going to get a lot of questions in the Q&A from a lot of steelmakers. Next, we'll have Thomas to talk about SSAB and the hybrid project. Let me just remind everybody, you can send questions through the control panel. And also we've received a few questions asking about the slides. Yes, everybody's going to receive the slides after the webinar. And the video, the recording will also be available. Thomas, floor is yours.
Thank you. I feel a little like an anticlimax after these two excellent presentations that actually cover quite a lot of what I was going to talk about also. So let's have this maybe as a quick recap. I'm not going to make a huge presentation about SSAB, but just to point out a few facts. We are a Scandinavian, Swedish, Finnish steelmaker, and we also have some operations in the US. A fairly tiny company located in the middle of nowhere in Northern Europe. But we are large insofar that we are the largest single CO2 emitter in Sweden. We make up 10% of the Swedish CO2 emissions, and that is something that we want to change. And you can also see as a side remark here that we cover most of the world with our niche products. And when it comes to the niche high strength steels, a little matter of, depending on definition, we cover almost a third of the world market, which we are a little proud of being a small steel maker. But if we, just as a bit of background, talk a bit about why we need to also address the issues of the steel industry, we should also remember that the steel consumption in the world is increasing, and it's increasing quite fast. It has almost tripled since the start of this century, from around 750 million tons per year in the year 2000 to 1.9 billion approximately this year, which is due to the fact that we have an increased standard of living in the world, we have a growing world population, we have a growing urbanization, we have growing needs for infrastructure and transportation, all of which drives steel consumption. And this growing steel consumption is also the reason why recycled steel, recycled scrap metal, can't cover the world demand of steel. Right now it covers around 25–30% of the world steel demand. The rest then needs to be made from virgin materials, from iron ore. And even though we expect the percentage of recycled material to increase to 50% in 2050, the remaining 50% still needs to be made from iron ore, and that's actually slightly more than the iron ore based steel production that we have in the world today. And that is why we need, as Steve pointed out earlier, to decarbonize the iron ore based steel making in the world. And that's what we have set up to do at SSAB also with our hybrid technology. In fact, we have communicated two objectives to our customers and other stakeholders. We are going to put fossil-free steels made without fossil CO2 emissions on the market as a commercial product on commercial terms in 2026. And already 2015, we said, as was indicated also on Steve's slide, that we're going to be an entirely fossil-free steel company by 2045. But actually the development around us, the politics, the demand from our customers and also ourselves, we have been developing much faster than what we dreamt. So earlier this year, we actually told the world that we are accelerating our decarbonization process, and we will be a largely fossil-free steel company already by 2030. And this is based then on using hydrogen-based steel making. If we look at the conventional blast furnace on the left-hand side here, that is the main culprit when it comes to CO2 emissions. And for those among us that aren't metallurgists, the background of this is that our raw material, iron ore, is pretty much iron oxide, and in order to get to the iron, we need to remove the oxygen, which then, since the blast furnace was invented in 1300 something, has been done with carbon in the form of coke. And what happens then is that the oxygen moves to carbon and forms CO2, and we're left with the iron, which is what we want. But this also means that for every ton of iron that you make, you get at least 1.5 tons of CO2 as part of the deal, often a little more actually, even though we're generally speaking rather good at this in Europe, and at SSAB we're rather close to this lower limit of what is even theoretically possible. But in the future, what we want to do is to expose instead the iron ore to hydrogen. And what happens then is that the oxygen in the iron ore moves not to carbon and forms CO2, but to hydrogen and form H2O, also known as water, as a byproduct. And we have the advantageous situation in both Sweden and Finland that we have a virtually CO2-free power grid, which means that we can use electricity to make hydrogen out of water with electrolysis, like Nell just talked about. Hydrogen that we can store, if we like, it's a storable commodity, but hydrogen that we can then put into our process, and then we get the water back as a byproduct again. As a side remark, the clever thing with this is also that we have already today, especially in the summer, when the sun is shining, the wind is blowing and the rivers are full, the situation that we produce more electricity than we can use in this country. And then we could use this excess electricity to make a lot of hydrogen that we can then store and use as it is needed in our own processes. And vice versa, on a cold, dark winter night with little electricity available, we can take our load off the network, stop making hydrogen, and instead use hydrogen that we have already produced and stored. And that way, in the future, we can not only make fossil-free steel, but also help to make sure that we can utilize every drop of renewable electricity that we have in the system, which I think is a little cool, if I may say so. Now, the end product from the classic blast furnace is liquid iron. It, literally speaking, runs in a trough on the floor in our steel shops. When you're using direct reduction and hydrogen, you get a, in comparison, rather unglamorous, boring gray lump of iron called sponge iron, a solid. And in order to process that further, we need to melt that down to liquid form. And to do that, we use exactly the same technology that is used for recycled scrap metal today. We put it in an electric arc furnace and use electricity to melt it to liquid form. But once we have, and this is important, once we have crude steel, all the downstream processes, the alloying, the casting, the heating, the rolling, the heat treatment, if any, and so on, those downstream processes are going to be exactly the same as they are today, just making sure that we're utilizing fossil-free electricity and fossil-free fuels in these processes. And it is in these downstream processes that we're creating the properties and performance of our steels. And since these processes are going to be the same in the future, we can confidently say that our steels will have at least the same performance in the future as they do today, just with the added value of being fossil-free, made without fossil CO2 emissions. If we take a quick look at the time schedule here, we have built, as Nell actually showed already, a pilot plant for making fossil-free sponge iron. This is a technology that has been known in the past, but really only on laboratory scale, and nobody has done this in an industrial environment, and that's what we wanted to learn to do in an optimum way. So this plant was inaugurated in 2020, and as you saw earlier, in 2021 we also rolled the first fossil-free sponge iron, or we rather melted it into steel and rolled it into steel plates. And we will continue to use this pilot plant up until 2025 or so in order to learn as much as possible. We've also made a pilot for storing hydrogen. We're doing this in underground rock caverns, which is located 30 meters below ground next to our plant in Luleå, northern Sweden, next to this pilot plant. And we are also now in the preparation stages for building a demonstration plant, a full-scale industrial plant with a capacity of more than 1 million tons of steel that will go into production in 2026 in time for those commercial deliveries that we have committed to making. And at the same time, we will at our Oxelösund facility have built an electric arc furnace that can then actually also melt the sponge iron so that we can turn it into steel. And what is more important, at the same time, we will close down the 2 existing blast furnaces that we have at this facility so that we're ready for those commercial deliveries to commence in 2026. And then in the coming years, we will step by step close down the remaining SSAB blast furnaces to be this 100% fossil-free, or at least largely fossil-free steel company by 2030. And we have here a shot of the location for the demonstration plant. It will be based next to one of the LKAB, our iron ore supplier and partner in the hybrid venture mines in Gällivare, northern Sweden. It will have a capacity of 1.3 million tons of sponge iron in the first stage, roughly corresponding to the same amount of end products. And we will a little more than double that then until 2030. And we believe that putting it next to the mine, we have synergies in terms of logistics, transportation, electricity supply, and so on, and also being close to the actual pelletizing plant where LKAB is then turning the iron ore into iron ore pellets, from which we're then making fossil-free sponge iron. And we are producing a little already today, as we have also seen. This is then the first plate that was rolled. It was delivered to the Volvo Group in a small ceremony in August 2021. And a little later in October 21, Volvo also showcased the so-called Tara, autonomous, so driverless electric mine truck. Little earlier this year in May, also this articulated dumper, which is now in commercial use by one of the construction companies in Sweden, built from fossil-free steels. And if you're buying an electric heavy truck from Volvo today, there are good chances that the chassis beams are made of fossil-free steel as well. And actually, we have a few other companies that have joined forces with us to work a bit closer when it comes to preparing their customers for fossil-free steel deliveries in the future. You can see that quite a few of them are in the automotive sector, which is not really a surprising fact. The passenger car is in the process of being getting rid of the tailpipe emissions right now, which means that the remaining carbon footprint is almost exclusively related to the materials that are being used in the car. For ESA and Autoliv are automotive sub-suppliers. We also here see some construction companies and also, for example, Cargotec, that makes everything from harbor cranes to forklift trucks. I thought I'd also mention, for example, Polestar, who is having a very ambitious project of creating a truly climate neutral car by 2030, which they've chosen to do with fossil-free steels from SSAB. Another company that you may have heard of is Mercedes-Benz, that has a very ambitious goal called Ambition 2039 of becoming carbon neutral, and they have recently also tested our fossil-free steels in a 1500 high-strength automotive steel, where they were happy to communicate that they can confirm that these have at least the same properties as conventional materials. All of which is our way of sharing a little of what we do. In the unlikely event that I haven't bored you to death already, you can also look at ssab.com/fossil-free to know all about our fossil-free journey going forward.
Thank you, Thomas. We're all awake. You haven't bored us at all. And if I may say so, for, as you said, a small steel maker, what you guys are doing is impressive. Thank you.
Thank you so much.
Now, last but not least, please let's hear from Stefan Tondo and hear the decarbonization strategy in one of the largest steel makers in the world, ArcelorMittal. Thank you, Stefan.
Thanks, Gabriela, and good afternoon, ladies and gentlemen. So I will not repeat what Thomas said, because steel is a steel being made in Sweden or in Spain or in France. So the basics of metallurgy remain the same, but I will try to focus a bit more on what are the hurdles we see for implementing hydrogen in the steel making. That's a project we all have in Europe, but it's not a fully free way, and we still have a lot of work to do. So I will more develop on these aspects. Some reminders, nevertheless, first. Yeah, as Thomas mentioned, steel is a large emitter of CO2 in the industry, but steel is also a necessary material, and we have seen that also in the presentation of Steve. The demand for steel will continuously be growing, and will be not only growing, but will be required to ensure the decarbonization of other sectors. There is no wind power without steel. There is no solar energy without steel. Even the electric cars need electrical steels, what we call magnetic steels, for their engines to work. So without steel, there is no decarbonization of the rest of industry. So this is why we are confident that the steel sector will continue growing. And as mentioned previously, we need to make sure that this steel is also being decarbonized and not transferring the burden from one sector to the other. So ourselves as company, we have very early committed to decarbonize our production. Our target announced already some years ago was to be net zero in 2050. We had also announced a reduction of our scope 1 and 2 in Europe of about 35%. But as you will see, as many other steel makers in Europe, the rules, the regulations, and especially Fit for 52 has changed a lot of things. This pushes everyone to be quicker, to decarbonize quicker, and thus we expect the global steel industry, and especially the European one, to go beyond that target. Obviously, it's important that facts, figures do not remain green claims, and we commit to the Science Based Target Institute and methodology to make sure that we are, as a steel maker, following the right pathway to go to this net zero steel emission in our production in 2050. So, a very quick reminder on why hydrogen is needed in the steel industry. So you know that today a large portion of the steel industry is made out of blast furnace, what we call the primary production route, using iron ore and coal. We just heard that the iron is naturally oxidized, so we still need to take this oxygen away, and today it's the coal which does this operation. And the consequence, unfortunately, is the production of CO and CO2. That's why we want to change using hydrogen. We're changing our assets to direct reduction plants. We would replace the use of coal by the use of hydrogen, which will enable to produce water mainly on top of the iron that we will then melt in electric arc furnaces. The pathway is almost the same for a lot of European steel makers, which are following a very similar way, and this should lead to a level of decarbonization around 90%. So hydrogen is really key to make this first very important step. There could be a second step, because we do not go to the full decarbonization doing that. There is still a certain portion of CO2 remaining in the loop for various reasons that I will not develop here. But there could be an option to capture the remaining CO2, and instead of letting it go to the atmosphere, there are solutions that, with the help of bacteria that digest this CO2 but need also hydrogen, to produce some chemical components like ethanol or some methanols that could also be used, for instance, as fuel for other industries, being aircraft industry, being maritime industry when it comes to methanol, or even basic chemistry. So these are the two main production steps where hydrogen may have an important role in the future and in the pathway of steel industry to its decarbonization. Can someone move the slide? Okay, thank you. Was not moving. We heard from Steve figures before. These figures that I'm presenting to you are slightly different because we have the reasoning always for a 2.3 million ton direct reduction plant, which is the classical side that is raising on the market. And you see here that for a 2.3 million ton direct reduction plant, the quantity of hydrogen needed is 150 KT. This is a huge quantity, as we have just heard. This could be also complemented by additional needs that could be for other reheating operations in our cycle, or as I just explained, for transforming the remaining carbon in chemical molecules that could be used by other industries. And you definitely need additional power generation to feed the electrolyzer that will produce the hydrogen. It is very important, and this will lead to the discussion on which kind of hydrogen is needed and which kind of electricity. You see that depending on the electricity which is installed, the quantity of installed capacity is very depending on what you're targeting. For instance, for 1 gigawatt electrolyzer, we would need roughly 20% more coming from a continuous production, coming from a classical energy production. And this could be, for instance, nuclear power in some countries. Due to the load factor and the intermittency of the production of the wind energy, you should roughly double that installed capacity to reach the same at the end. And for solar, it's even more than 4 times more to have the same base load in terms of electrolysis capacity. So depending on where you produce, the role of the electricity will have a very strong impact. On the right side, you see some figures that were presented by the European Parliament Research Service, which made a study on decarbonizing steel. And you find similar elements with for 1 million ton of steel, you would need 0.70 KT of hydrogen. We also consider that roughly 60% of the steel production is already currently using electric arc furnaces. That's also what Thomas developed before. So this portion, if moving to green electricity, will be already decarbonized. But the 60% remaining, which are the primary production route, this could over time or should over time be converted to reduction processes using hydrogen, mainly in Europe. We'll go to the next slide. So when will the European production be decarbonized? I'm not doing here a focus here on ArcelorMittal. We have our plans as our competitors do have. But if you read what's announced in the press as decarbonization plans, if you read what is requested as subsidies by several steel makers to national or European authorities to allow their transformation, you see that by 2025 to 2030, at least, and I say at least 50% of the classical primary route will be already fully decarbonized. If you this represents so 60% of 150 million ton, so you're at 84 million tons of steel that will be already decarbonized, plus the 66 million ton which are already using electric arc furnaces to remelt recycled steel. So you come at roughly 108, 110 million tons decarbonized between 2025 and 2030 out of the 150 million tons. So steel will be decarbonized very shortly. But obviously, this can be reached only if we have the hydrogen which is available to enable this heavy transformation from the classical blast furnaces to the direct reduction plants. Today, to give you some figures about what would be the ramp up, I will start from the study on the right side, which was a study from Eurofair done in 2019. And they were saying, based on elements available at that time, that 1.73 million tons of hydrogen would be used in 2030. And the level of hydrogen to be required in 2050 would be at 5.5 million tons. This represents in 2030 roughly 149 terawatt hour electricity additional to what we consume today. And for the whole steel industry, for electrolysis plus the electric arc furnaces, we would go to roughly 630, 635 terawatt hour in 2050. So the global quantity of electricity needed to melt the steel, but also to produce the hydrogen to decarbonize it, is 7 times higher than what we are currently using today, being already an electricity-intensive industry. On the left side, you see a different study produced by a specific institute, which shows that on a worldwide basis in 2030, we would need 8 million tons, but Europe representing half of it, it's already 4 million tons. So you see the ratio between Eurofair being in 2018 at 1.7 and MPP at 4. So this to give you an idea of the magnitude of the hydrogen needs in the very, very short term. If I go to the next slide. Sorry, there seems to be some lag. Yeah, I've just spoken about the needs for hydrogen. What is hampering us to go to that level today? Why don't we have more hydrogen available? So first of all, what we need as steel producers is to have obviously a high availability of hydrogen. We will need a big stability of the hydrogen supply. I will develop these points immediately. This hydrogen will need to be decarbonized, otherwise we replace the fossil fuel by a non-fossil free hydrogen, so we will not have any savings. And it needs obviously to be affordable to replace the current energies it is going to replace. In terms of availability, the first concern we have is, are the production, the needs we will have match with the production which is coming on stream? And if not, should there be a prioritization per sectors? A lot of sectors are fighting for the first ton of hydrogen. In terms of legislation, there is still a lot to be done for the transmission, for the storage, and regulation is not helping the supply of hydrogen in a stable way to the steel industry. A lot of regulation is still missing for hydrogen. We are just discussing at European level what should be the hydrogen and decarbonized gas packages. So even for investor in the hydrogen business, all rules are not clear, and especially for transmission storage, it's quite difficult. Then being decarbonized, obviously we need to know what decarbonized steel and decarbonized hydrogen means. There is a definition for green hydrogen, which has just been released by the European Commission. We still don't know what low carbon hydrogen means. So is hydrogen made on a grid where CO2 is at 20, 30, 50 kilograms CO2 per ton sufficient? Is it low carbon hydrogen? This is still not clear. And last point, obviously the affordability. Today, steel is traded on the global market, needs to be competitive. We have different taxations linked to CO2 in the various regions, and especially in Europe. So if we want steel to be able to export our steel, and we just heard SSAB selling a lot of specialties around the world, it's the same for us. So export is an important factor to the steel industry. We also need to be competitive, meaning that hydrogen should be affordable compared to the produce it replaces, and especially coal or natural gas. And last point, if it's not the case, at European level, we need to find, national level, we need to find subsidies mechanisms to compensate the overcost of hydrogen in the specific country linked to the specific energy production methods, sources, to compensate and keep it affordable. Thank you.
Thank you, Stefan. That was very thorough. And you covered a lot of our questions on your few slides. I know seeing me puts a lot of pressure on time, but yeah, thank you, you did a great job. So now we're going to start our, I would like to invite our panelists to start our debate. I am afraid we are running a little bit late, so we'll have 5-10 minutes. Just before we start, can we please have the poll and have a question to start the discussions? Everybody can vote through the control panel. The question is, when do you expect hydrogen to be widely used in steelmaking? You can choose one answer: in 10 years, in 20 years, in 30 years, or never. Again, get your vote in and let us know, when do you think hydrogen will be widely used in steelmaking? And we've got about 20 seconds, and we'll shortly have the result and start our discussions. Is the results coming up? 10 years, 20 years, 30 years. It's nearly there. 80% of attendees voting. Can we have the results, please? Okay, 53%, so more than half of our attendees expect in 2 decades, around 2040. Would anybody like to jump in and discuss? Is this a surprise? Is this expected? Is it realistic? Let's start the discussion. Who wants to go first? Thomas, I think you are muted. Okay, can we try now?
Okay, now you can hear me, I hope.
Yes.
The organizer was muting me, so I must have been misbehaving somehow. I deeply apologize. But we are rather clear on the fact that we are going to do this in a bit more than 1 million tons in 2026, actually. That is going to happen. But I agree, it takes time. And I have also to admit that we have a good situation insofar that we have access to green electricity and thereby green hydrogen also, which is more difficult on the continent.
Håkan, anything from you?
Depends on what you mean by widely used. If we mean widely more than 50%, then my guess would be 20 to 30 years. But I think we will see the first large-scale projects in 25, 26, and there will be a number of them leading up to 2030, and then, you know, depending on the cost and the availability of renewable power, I think we will see, you know, more and more green steel being made. But we have a tendency to be over optimistic in the short run and be pessimistic in the long run. So I think the same is true here. I think there will be challenges in getting power. That is the main bottleneck. We are moving too slowly. Permitting takes 5, 6, 7 years. Both for wind and solar, it's going to take forever to get that power. We have a scale up to do, you know, on the electrolyzer side. People will make wrong decisions on technology. The DRI technology has to mature. You need to find offtake at a higher price. So lots of barriers, but I'm a long-term optimist and a little bit more, maybe not negative, but a bit more cautious short term.
Thank you.
I think maybe one thing that deserves to be said also, we're talking a lot about the large amount of electricity that needs to be made available, but we should also be aware of the fact that the energy consumption using hydrogen and direct reduction is actually lower than the energy consumption we have using blast furnaces. It's just that we add the energy in form of coal right now. A blast furnace is pretty much a large carbon power plant with a bit of steel as a side product. And I think that is something that we should also remember. So what we really need to do, and what we're doing here, is decarbonizing our power system. And that is something that needs to happen globally anyway.
Mm-hmm. Yeah, I agree. And there will be a lot of other sectors trying to electrify. And do you think the steel sector would need to invest in their own sources of electricity? And perhaps this is a question for Håkan. As a steelmaker, what would you consider to choose where you put your hydrogen plant, and how to decide on which technology you would implement in terms of electrolysis?
I'm not a steel maker, so maybe you should pose that question to
So Stefan or Thomas, where is it best to place an electrolyzer?
Yeah, I can answer that one indeed. First of all, everyone strategically has to invest in his own business. And when we are speaking about just ArcelorMittal, I think we announced that we would invest several billions in Europe, more than 5 billion in Europe. So that's huge amounts. And that's definitely our priority. That's what will transform our core business. And I think it makes sense for us to verticalize as steel makers only when we are not sure that we have a reliable source. Investing in a new direct reduction plant, if you are not sure to get the right quantity of hydrogen in a stable way and at a decent price, then you have a concern. If you have suppliers which are able to support you in that way, and it's really depending on the region, to be clear, then you have or you don't have to do it.
Mm-hmm. Steve, let me go to you now. Do you think that the decarbonization route in the steel industry is going to be color agnostic, or is there going to be a dominance from one type of hydrogen and then move on?
That's a good question. You're right. A lot of people are intrigued by this. I think in the long run, obviously, the objective is to get to green hydrogen. I mean, anything else is a compromise, but I don't think it's certainly going to be a just a simple one focused race. Inevitably, a lot of regions have access to natural gas, and depending on the availability essentially of that and other raw materials, then that with carbon capture makes a lot of sense. The US obviously is an example of that. So I think we're going to see grey hydrogen in some situations, then blue, and then ultimately green. But we've heard a lot already about how that electrolyzer technology is still evolving and developing, and there are cost issues around that. So I certainly don't think we're going to see just entirely green hydrogen from day one. It's just not feasible.
Okay, interesting. Thomas, and perhaps Stefan too, how do you ensure your huge investments can be returned, selling at a green premium, let's say? And how do you make sure you have demand for that product? Is that going to happen differently in different regions? Is it through offtakes? How do you plan ahead?
Well, as I briefly showed, we have chosen to partner up with a handful of carefully selected partners that have high ambitions in this area themselves and see demand from their customers, so the end user. So I'm relatively optimistic. We can see that there is a demand for this. It varies a little. Europe is maybe on the forefront. You have North America, a little depending on where you are. There are certainly initiatives in Asia as well. But when it comes to end user demand, maybe Europe is the prime example. We also know that the closer to a consumer product our customers are, the clearer the demand is. I think I showed a lot of automotive companies, and that makes sense. Without tailpipe emissions, you have the carbon footprint from the materials, and especially when it comes to hybrid cars, I think people are aware of this. There's been a lot of discussions about rare earth minerals and rare earth metals and conflict minerals and so on. So that demand is certainly there. On the opposite scale, maybe a farmer that has a fossil-free combined harvester probably won't get a better price for his milk. You lose the visibility. And sometimes people are screaming for legislation or incentives or whatever. And I think that what we really need is transparency. If we can make it clear to the consumer or the steel buyer what type of steel we're offering and what the environmental performance is, then I think the demand is there.
Right. Do you agree, Stefan?
I will slightly complete and redraft your question maybe. Customers, market understands that for a green steel, there are higher costs linked to the investment, linked to the new energies that we will need. Hydrogen, we just discussed it, is rather expensive. But what's the right choice between buying a product which is maybe a bit more expensive but decarbonized, or paying the same price for the product which is not decarbonized because there are high CO2 costs attached to it? So I think from a customer and a market point of view, the choice is quite simple.
So I'm conscious that we're running out of time. I just want to do a last question, quite in line with a few attendees' questions here, and you touched up a bit. The electrolyzer manufacturer scaling up technology, and Europe is also incentivizing in a way their own electrolyzing manufacturing capacity to be able to, meet demand. The steelmakers are looking into different ways and investing in different alternatives. So what more can the government do in terms of incentives, in terms of framework, and to kind of accelerate this decarbonization? It seems it's a bit patchy. Some in Europe, there's more movement, and in some countries there isn't, and some think that in Europe still there's more to be done. What do you think that needs to be done?
I can start on that. I think when you look at hydrogen, the best place to produce hydrogen on the planet today is the US, and it's due to the IRA, where you get up to $3 per kilo. It's not crystal clear, but it provides sufficient transparency on what to expect in terms of subsidies. So if you are a project developer or if you're a steel manufacturer, you know what you're going to get. If you look at Europe, we have started not with the carrot, we start with the sticks. So we force these regulations in terms of emissions and how much you have to decarbonize by when. And we go back and forth on should it be 30%, 35% by 2030 or 2035. So we're still on the ambition level. It's the same way with renewable energy. Oh, we want to build 120 gigawatt of wind power. Yeah, that's a nice target, but what are we doing, in order to get to that? We haven't, done anything on the permitting timelines. We haven't sort of allocated space for it. We haven't, done anything. We were just talking targets, which I think is good because it creates demand and it can put the price on not complying with it. So yes, we all have good intentions, but at the end of the day, money matters. So you need some kind of mechanism to force demand. But what is lacking on the incentive side is that it's a patchwork of mechanisms. It's IPCEI funding. It's the hydrogen bank. It's this and that. But still, there's very limited transparency on how are companies going to access these funds. There's no certainty around it. When you build your business case, you cannot bank on getting this money. So first of all, I think the level of subsidies is way below what the US has announced. Second, it's a very bureaucratic approach, so it's difficult for companies to apply for these grants. They have to complete 400-page documents, and then they have no clue whether they will be selected. The bureaucrats select the projects, not the market. And I think, for the EU to catch up, we need more clarity. It doesn't have to be perfect, but we need a mechanism. So can they take some of the current initiatives and transform them into some kind of IRA type mechanism so that the steel manufacturers, the ammonia producers know that they will get some, help on the initial tonnage, because that will be expensive. Over time, we have to do without subsidies, but right now there's lack of transparency and clarity, and that's what they need to do.
Excellent. Anybody else?
Well, unfortunately, I would have to say the same thing. We know that the technology works. Now it's all about scaling up, starting building things, and so on, and that takes too much time. I think we need to learn to do things in parallel rather than having different authorities waiting for each other.
Collaborations must be key. Thank you so much, guys. It's been amazing. I'm sorry we've run out of time, and I know how busy you are, and I can't keep you any longer. I really want to thank you for all the insightful discussions here, and thank our attendees as well. And if you're interested in finding out more about our products and how we can help you to understand hydrogen developments around the world, please get in touch for a free trial. We're also hosting a Green Strategies networking event in London in January, so it would be great to see you there. But for now, take care and see you next time.
Thank you.
Thank you. Bye.